Okay, hello, hi, welcome back to Math 250. Okay, so welcome to Math 250. Hello. Today's lecture will be in two parts. The first part, which will be a short part, will be a short lecture on exponential functions. And the remaining time, which should be the longer part, should be at least 50 minutes, I will work through the homework 1 questions. Okay, so today's lecture will be in two parts. So today is in two parts. Today's lecture will be in two parts. The first, which should be a short part, will be basically I lecture. It'll be a lecture, it'll be a short lecture on exponential functions. Lecture on exponentials, okay? Exponentials or exponential functions. Okay, so today, the first short part will be a lecture on exponential functions, and the remaining time, the second longer part, or the remaining time, will be me going through homework questions. Okay, going through the homework questions, which will be due. I think it's due this coming weekend. So the remaining time, which should be at least 50 minutes, I work through homework 1 questions. Homework 1 questions. And by the way, let me remind you that the full solutions to homework 1 are in PDF form and on Moodle already. But it may be helpful if I also go through it in lecture. So then in the second longer part of today's time, I'll be going through homework 1 questions. Okay, so those are the two things I'll be doing today. The first short part, lecture on exponentials, and the second, a longer part, work through homework questions. Okay, so for the first part, okay, is the writing clear? I just want to check that the writing is clear. Okay, the writing is sort of clear. Okay, so the first part is exponential functions. Exponential functions. And what is an exponential function? What's an exponential? Well, an exponential function is just a function that has the form of an exponent. Okay, that's all. Okay, an exponential or an exponential function is a function that has the form of an exponent. Okay, it's the function with the form of an exponent, and the input variable is in the power. Okay, the input variable is in the power. Okay, so here's the precise definition. A function p equals to pt. So here, the input variable is t, and the output variable is p. Okay, here, the variable for the input or input variable is t, and the output variable, the variable for the output, is p. So function p equals to pt is an exponential function, or is an exponential function with base a. So it's an exponential function with base a, basically, if it has the form of an exponent. Okay, it's an exponential function with base a, or an exponential if it has the form of an exponent. Okay, that's the key thing. It has the form of an exponent, and the input variable t is in the power. The input variable is in the power. So, more precisely, if it has the form pt equals to p naught times a to the t. Okay, p naught times a to the t. So in other words, it has the form of an exponential. if it has the form of an exponent. It has the form of an exponent, and the input variable t is in the power. And what's P naught and A? P naught and A are just concrete numbers, are specific concrete numbers which are strictly positive. So where P naught and A are specific concrete numbers which are strictly positive. So they're strictly positive constants. Okay, so this is the definition of an exponential function. So essentially, it's a function that has this form. It's a function that has the form of an exponent. It's a function with the form of an exponent, and the power, the input variable is in the power. The input variable is in the power. Okay, it's a function with the form of an exponent. Okay, and P naught and A are just concrete numbers that are strictly positive. Okay, so they're strictly positive constants. Okay, so it's a function with the form of an exponent. Okay, let me give you one concrete example. So, for example, pt equals to 3 times 2 to the power of t. This is an exponential function. This is an exponential function. Okay? This is an exponential function, or I'll just write exponential. Okay, so this is an exponential function, right? Because this is an exponent. This an exponential function is something with the form of an exponent, so it's an exponent. And the power, input variable is in the power. The input variable t is in the power. Input variable is in the power. So this is an exponential function because it has the form of an exponent, essentially. And you can see what are the concrete numbers P naught and A. Well, you can see over here that P naught is equal to 3, and the base A is equal to 2. Okay, I just killed this marker, so let me just throw this away. Okay, so this is an exponential function. Okay, this is because it has the form of an exponent. It has the form of an exponent, and the input variable is in the power. Okay, so there's one concrete example. And by the way, before going on, why do I use t for the input variable and p for the output variable? Okay, why do I use the letters? Why do I use these letters? Why do I use the letter t for the input variable, and why do I use the letter p for the output variable? Okay, why do I use these letters t and p for the output variable, t for the input variable, and p for the output variable? So why do I use these letters t and p? Well, one reason for that is that one common basic example is population growth. Okay, we're often interested in population growth. Okay, that's one of the basic examples. Because remember, what is this course? What is this course? This course is calculus for business and the social and biological sciences. Okay, so that's what this course is. This course is calculus for business and the social and biological sciences. And so one of the basic examples, not the only example that's interesting, but one of the basic examples is population growth. Okay, one of the basic examples is population growth. And that's why we use the letters t and p. T for the input variable and p for the output variable, because we're often interested in the case where t is for time and p is for population. So t, input variable t, often for time, and p, output variable p, is often for population. So because of the nature of this course, one of our basic examples is population growth, and oftentimes t is for time and p is for population. Okay, oftentimes t is for time and p is for population. That's not always the case. Okay, there are other interesting examples of exponentials too. Okay, there are other interesting types of word problems that we'll be interested in too. But one of the basic examples, not all the basic examples, but one of the basic examples, because of the nature of this course, calculus for business and the social and biological sciences, one of the basic examples is population growth. So and so that's why we use the letters t and p. Okay? Of course, this doesn't always mean t doesn't always mean time, and p doesn't always mean population, but for many examples it will. For many examples it will. Okay, now for these exponential functions, there are two cases. There are two cases. The first case is where the base A is strictly bigger than 1, and that's the case of exponential growth. Okay, that's the first case. And the second case that we're interested in is the case where A is strictly less than 1, and of course it's always strictly positive, and that's the case of exponential decay. Okay, that's the case of exponential decay. Okay, for exponential functions there are two cases. The first case is the case where the base A is strictly bigger than 1, and that's the case of exponential growth. And the second case is the case where A is strictly less than 1. Of course, A is always strictly positive. That's an initial requirement. And that's the case of exponential decay. Okay, let me check to see if all the writing is clear. Okay, it looks like all the writing is clear. Okay, so let's continue. So let's draw the pictures for these two cases. Let's draw the pictures for these two cases. So pictures. So first, we're going to look at the picture for the case A is strictly bigger than 1. And remember, so this will be the picture for exponential growth. Exponential growth. Okay, so that'll be the picture for exponential growth. Okay, so the horizontal axis is in the input variable t, if you prefer, for time. And the vertical axis is in the output variable p, if you prefer, population. Let me draw this t a little bit higher. Let me just draw the horizontal axis a little bit higher. It's better if I drew the horizontal axis a little bit higher. Let me draw it this high. Okay, so the horizontal axis is in the input variable t, and if you prefer, it can be time, though it doesn't always need to mean time. It can be other things too in word problems. And the vertical axis is in the output variable p. If you prefer, it can be in population. It can be in population, but it doesn't always mean population. Okay, there are word problems where it doesn't mean population. And so we want to graph this exponential function. We want to graph this exponential function. We want to graph this exponential function in the case where the base A, where this base A is strictly bigger than 1. So in other words, it's the case of exponential growth. It's the case of exponential growth. So first, at time t equals to 0, the value is p naught. So the initial population, or the initial quantity, is p naught. And that's very easy to see. You just plug t equals to 0 into this function. If we plug t equals to 0 into this function, we get p at 0 is equal to p naught times a to the power of 0. And remember, anything to the power of 0 is 1. Anything to the power of 0 is 1. Okay, can you see this? You see this? Yeah, you can see this. Yeah, anything to the power of 0 is 1. So this should be a 1. So that's p naught times 1, which is equal to p naught. Can you see this? Okay, so if you plug t equals to 0 into here, plug t equals to 0 in here, we just get p naught times a to the power of 0, p naught times a to the power of 0. Anything to the power of 0 is 1, So P naught times 1 is P naught. So the initial population, if you want, or the initial quantity is P naught. This is P naught. And what happens is that for exponential growth, as you move forward in time, okay, for exponential growth, as you move forward in time, the function blows up to infinity. The function blows up to infinity. So for exponential growth, as you move forward in time, the function grows to infinity. It grows to infinity because it's exponential growth, or if you prefer, it blows up to infinity. And a shorthand way of writing blowing up to infinity is you write pt goes to infinity, blows up to infinity as we move forward in time. Okay, so as we move forward in time, the function blows up to infinity, or the function grows to infinity for exponential growth. And as we move backward in time, the function decays to 0. The function decays to 0. So then that's the picture for exponential growth. The horizontal axis is in the variable t, and sometimes it means time. Okay, in many cases it means time, but also there are cases where it doesn't mean time. The vertical axis is in the output variable p. In many cases it means population, but doesn't always mean population. There are cases where it doesn't mean population. The initial quantity, or if you prefer, the initial time at t equals this, the initial population at time t equals to 0 is p naught. Okay, is this p naught? And for exponential growth, as you move forward in time, the function grows to infinity. Okay, so as you move forward in time, the function blows up to infinity. And as you move backward in time, the function decays to 0. Okay, the function decays to 0 as we move backward in time. So that's exponential growth. Okay, that's the case of exponential growth. Okay, so now, so that's the picture for exponential growth. Now let's look at the picture for exponential decay. Let's look at the picture for exponential decay. Okay, so the case where a is strictly less than 1, of course it's always strictly bigger than 0. This is the case of exponential decay. And basically, the picture for exponential decay, okay, let me check to see if this is clear. Okay, it looks like it's clear. The picture for exponential decay is just you take the picture for exponential growth and you flip it. Okay, you take the picture for exponential growth and you reflect it about the vertical axis. Okay, that's the picture for exponential decay. You take the picture for exponential growth and you reflect it about the vertical axis. Okay, so again, the horizontal axis is in time t, is an input variable t, if you prefer time, sometimes it means time. Again, the vertical axis is an output variable p, and sometimes it means population, though not always. And what you want to do is you want to graph exponential function pt equals to p naught times a to the t. You want to graph this function for the case where a is strictly less than 1, the case for exponential decay. And at time t equals to 0, the quantity, the initial quantity, or if you prefer, the initial population is p naught. Okay, so at time t equals to 0, the initial quantity is this p naught. And the reasoning is the same as in the case of exponential growth. Okay, it's the same computation as in the case of exponential growth, exactly the same computation. By the same computation as that for exponential growth, at time t equals to 0, the initial quantity, or if you prefer, the initial population, is p naught. And in the case of exponential decay, as you move forward in time, the function decays to 0. Okay, as you move forward in time, the function decays to 0. So this goes down towards 0. This goes down to 0 as you move forward in time. Okay, decays to 0 as you move forward in time. And the shorthand way of writing it is you write this. Pt decays down to 0 as we move forward we move forward in time. Okay, so this is a shorthand way of writing that the function decays to 0 as we move forward in time. So the function pt goes down to 0, decays to 0 as we move forward in time. Okay, this is just a shorthand way of writing of expressing this picture. And for exponential decay, as we move backward in time, okay, for exponential decay as we move backward in time, the function blows up to infinity. Okay, so that's the picture for exponential decay. At time t equals to 0, the initial quantity, or then if you prefer the initial population, is p naught. For exponential decay, as we move forward in time, the function decays to 0. As we move forward in time, the function decays to 0. And as we move backward in time, the function goes up to infinity. So the picture, so as I said, the picture for exponential decay is basically you take the picture for exponential growth and you flip it. Then you take the picture for exponential growth and you reflect it about the vertical axis. You flip it about the vertical axis, take the picture for exponential growth and reflect it about the vertical axis, and you get the picture for exponential decay. You get the picture for exponential decay. Any questions? Any questions about this? Okay. Okay, before going on, let me just give you some examples to build some intuition for exponential growth and exponential decay. Okay, let me give you some examples to build intuition for exponential growth and exponential decay. So this should be like some 5-minute examples. These are just 5-minute examples. So some examples to build intuition about exponential growth and exponential decay. And by the way, these types of examples are not the type of things that I would put on a test. Okay? So these type of examples are not test material. These are just things for you to do on your own to build intuition about exponential growth and exponential decay. So these are not test material. Okay, so these are not test material. This is, I might not even put it in the homework. Maybe I'll put it in the homework, or maybe I won't. But these are not the type of material that I would put on the test. This is just to give you some intuition, some intuition on your own for exponential growth and exponential decay. Okay, so example. Let's say you take the function pt equals to 1.01 to the power of t. Okay, this is 1.01 to the power of t. Okay, that's what this function is, 1.01 to the power of t, and you see that this is an exponential function. Okay, 1.01 to the power of t is an exponential function because it's an exponent. It's an exponent where the input variable is in the power. Okay, so this is an exponent, it's an exponent, and the input variable is in the power. So this is an exponential function. This is an exponential function. And what's the p naught in this case? The p naught is 1. And what's the base a? You can check to see that the base a is 1.01, which is strictly bigger than 1. Okay, the base a is 1.01, which is strictly bigger than 1. So then, since the base a is strictly bigger than 1, what do we have? We have exponential growth, right? From what we discussed previously, when the base is strictly bigger than 1, it's only slightly bigger than 1. It's only slightly bigger than 1, but it's still bigger than 1. So then from what we discussed previously, this is exponential growth. Okay? And then, so since it's exponential growth, that means from the picture that I just erased, as we move forward in time, the function should blow up to infinity. Okay? Exponential growth means that as we move forward in time, the function should grow to infinity. So the function should grow to infinity as we move forward in time. Okay? The function should grow to infinity as we move forward in time. That's exponential growth. The function grows to infinity as we move forward in time. The function blows up to infinity as we move forward in time. That's what exponential growth means. Okay, let's check this. So you check this by using a calculator. You can check this using a calculator. So as an exercise, check with calculator. Okay. Okay, check with a calculator that this function does indeed get bigger and bigger and bigger as we move forward in time. Okay, it should be blowing to infinity. It should be growing to infinity as we move forward in time. So check with a calculator that this function does get bigger and bigger and bigger as we move forward in time. So you can check that. Okay. P0 is approximately 1. Actually, P0 is exactly 1. That's not hard to see. It's not getting really big yet, but it's there. But it's not small. You can check that P10 is 1.1 is approximately 1.1. Check with a calculator that P10 is 1.1. So you plug t equals to 10 in here, you get 1.1. It's not getting really big yet, but it's still getting bigger. It's still getting bigger. And you can check with a calculator that P100 is approximately 2.7. It's supposed to be getting blowing up to infinity, so it should be getting really big. Well, it isn't getting really big yet. It isn't getting really big yet, but it's still getting bigger, right? 2.7 is bigger than 1.1. And then you can check with a calculator that P1000 is approximately 20,959. So now it's getting really big. It's really getting really big, and it should, because it should be going up to infinity as we move forward in time. So now it's getting really big, and now you can check that with a calculator also that P of 10,000 is now really, really big. P of 10,000 is approximately 1.64 times 10 to the power of 43. So now it's getting really, really big. So then you can see by numerical computations of a calculator, by plugging in numbers into t, that this function does indeed get really, really big as you move forward in time. That it blows up to infinity as you move forward in time. Okay, so you can check that using a calculator. Okay, and let me give you another example. An example with for exponential decay. Say this example. So here PT is 0.99 to the power of t, and you can see that this is an exponential function. This is an exponential function, right? Because it's an exponent. It's an exponent. It's an exponent, and the input variable is in the power. And you can see that P naught over here is 1, and exponential A is 0.99, which is strictly below 1. It's only slightly below 1. It's only slightly below 1, but it's still strictly below 1. So that's the case of exponential decay. That's the case of exponential decay. That's the case of exponential decay. And so since it's the case of exponential decay, remember what the picture of exponential decay does. The picture for exponential decay is that the function decays down to 0 as we move forward in time. As we move forward in time, the function decays down to 0. So we should have that the function decays down to 0 as we move forward in time. So that's the picture for exponential decay. That's the picture for exponential decay. And so then check that picture, check that this function doesn't indeed go down to 0. Decay gets closer and closer to 0. Check that this function doesn't indeed get closer and closer to 0 as we move forward in time. And you can check that with a calculator. Check that with a calculator. So exercise, check with calculator that this function does decay down to 0 as we move forward in time. So for instance, if you plug t equals to 0 in here, okay, it isn't very close to 0 yet, it's just 1. But if you plug t equals to 10 into here, plug t equals to 10 in here, you can check that this is approximately 0.9. It doesn't get closer to 0 yet. It doesn't get really close to 0 yet, but it's still smaller than 1. Okay, it's still smaller than 1, even though it isn't really that close to 0 yet. But if you plug t equals to 100, plug t equals to 100 in here, you can check that this is going to be approximately 0.37. So that's much smaller than 0.9. It isn't super, super close to 0 yet, but it's closer to 0 than 0.9. Okay, plug t equals to 100 into here. And if you plug t equals to 1,000, you're going to get, now it's very close to 0. 4.3 times 10 to the power of minus 5. And if you plug t equals to 10,000 in here, now it's really, really close to 0. You can check that this is approximately 2.2 times 10 to the power of minus 44. So now it's really, really, really close to 0. So you can see by numerical computations that you do indeed have that this exponential function, this thing over here, gets closer and closer to 0, decays down to 0 as we move forward in time. Okay, so you can check these things by numerical computations. Okay, I'm going to leave you to do it yourself. Okay, this is, as I said, this is not test material. These are just little things for you to do on your own to build up intuition. Okay, so now for the remaining time, we're going to go through homework 1. Okay, we're going to go through the homework 1 questions in the remaining time. And as I've said, as I've already said before, the PDF file containing all the solutions are already downloaded on Moodle. It's already on Moodle. Okay, so the PDF file containing the written solutions are already on Moodle. And but it may be good to have somebody talk it through. It may be good to have a person talk it through in a video lecture. So that's what I'm doing. Okay, so now we're going to go through homework 1 solutions. Okay, we're going to work through homework 1. And okay, so we're going to work through homework 1. I think today we can work through the solutions of all the questions. Okay, today we'll just work through the solutions to all the questions. Okay, so let's look at the homework 1 PDF file, question number 1. And what does the question number 1 ask for? What does question number 1 ask for? Here it is. Find the equation of the straight line that passes through negative 2, 1 and 2, 3, and then roughly sketch the graph. So find the equation of the straight line that passes through the numbers, the points negative 2, 1 and 2, 3. So the first part of homework 1 PDF file number 1 is to find the equation of the straight line that passes through these 2 points, negative 2, 1 and 2, 3. And then after that, roughly sketch the graph of the straight line. Sketch graph of the straight line. Okay, roughly sketch the graph of the straight line. Okay, let's do this question. First of all, before doing this question, note that this question is an example of principle 1. This question is the example of principle 1. 2 points determine a unique straight line. Okay, this question is an example of principle 1, which says that 2 points determine a unique straight line, right? Because we have 2 points over here, minus 2, 1 and 2, 3. And remember what principle 1 says. Principle 1 says 2 points determine a unique straight line. So if we have 2 distinct points, then there's one and only one straight line crossing those 2 points. Okay, if we have 2 distinct points, then we have one and only one straight line crossing those 2 points, namely this straight line. And basically, this question asks us to compute the straight line. Okay, this question asks us to compute the equation of the straight line. Okay, that's what this question asks. Okay, so towards computing the equation of the straight line, first, let's compute the slope. First, let's compute the slope of the straight line. And we have a concrete formula for computing the slope. That's the slope formula. So by the slope formula, the slope m is given, remember what the slope formula is. The slope formula from 2 lectures ago, the slope is given by y2 minus y1 over x2 minus x1. And what's x1, y1 and x2, y2? Well, we can take this point to be x1, y1, and we can take this point to be x2, y2. Okay, we can also flip it around. We can also flip it around, but let's do it this way. Take this point to be x1, y1, and this point to be x2, y2. So then, okay, is everything clear? Is everything clear? Okay, it looks like everything's clear. It looks like everything's clear. Okay, so we're taking this point to be x1, y1, and this point to be x2, y2. Okay, x1, y1, and x2, y2. So just plug this point into the slope formula. Okay, so plug these points into the slope formula, and we get y2 is 3, minus y1 is 1, divided by x2 is 2, and x1 is minus 2. Okay, so by the slope formula, this is what we get. Okay, so is everything clear? Is everything clear here? It looks like everything's clear. Everything looks pretty clear. Okay, and then we just continue computing. 3 minus 1 is 2. 2 minus 2 is 2 plus 2, which is 4. And so the slope m is 1/2. The slope is 1/2. So then, what do we have? We have the slope. We have the slope, and we have 2 points on the straight line. We have the slope, and we have 2 points on the straight line. And so to compute the straight line, we can just use the point slope formula. To compute the straight line, we can just use the point slope formula. So by the point slope formula, the equation of the straight line is y minus d is equal to m times x minus c. And we know what m is. M is the slope. And what's CD? CD is just any point on the straight line. It's just any point in the straight line. We can take this point to be CD, or we can take this point to be CD. Let's take this point to be CD. Okay, we can take the other point too, but let's just take this point. Okay, so plugging in this point and this slope into the point slope formula, we get y minus d, d is 1, is equal to m. M is the slope 1/2 times x minus c. What's c? C is minus 2. Okay? And by the way, in tests and homework, you can stop here. Okay? So you can stop here. Okay? In tests and homework, you can just stop here. But let's continue computing anyways. So y minus 1 is equal to 1/2. X minus minus is plus, so x plus 2. And so this is 1/2 x plus 1/2 times 2 is 1. So y minus 1 is 1/2 x plus 1. And then we just bring the minus 1 to the other side, so y is equal to 1/2 x plus 2. So that's the solution 2. So you can stop here. So you can take this as the solution, and also you can take this as the solution. So you can stop here, but you can also stop here. You can also stop here. You can stop here, or you can stop here. You can take this as the solution, or you can take this as the solution. Either will be fine. And let's sketch the graph. The graph looks like this. Say this is the x-axis, and this is the y-axis. So we have 1 point on the straight line, that's 2 minus 2, 1. And we have another point on the straight line, that's 2, 3. And then we're just looking at the straight line that connects these 2 points. So this is the straight line. So this is y equals 2, 1/2 x plus 2. Okay? Let me see if I did everything right. Okay, looks like I did everything right. Yeah, I did everything right. Okay, now let's do question number 2. Oh, okay, before I go on, let me say one thing, and that is, okay, before I go on, let me say one thing, and that is, in this example, I show a lot of work, and you don't need to, in tests and homework, you don't need to show as much work as I do. Okay, in tests and homework, you don't need to show as much work as I do. The main reason why I show a lot of work is for pedagogical reasons. Okay, I show a lot of work for pedagogical reasons. I'm teaching, and when you're teaching a lot of people at varying levels, you basically show every step. Okay, so since I'm teaching for pedagogical reasons, I show a lot of steps that don't need to be shown. Okay, I show a lot of steps that don't need to be shown. So in tests and homework, you don't need to show as much work as I do. Note, in tests and homework, you do not need to show as much work as I do. Okay, in tests and homework, you don't really need to show as much work as I do. However, remember that you still need to show some work. You still need to show some work, or even a little bit of work. You just need to show, you still need to show a little bit of work, because remember, in the test, if you just write down the answer and you show no work at all, then I'll give you 0. Or if you write down the answer and you show some work that's wrong or clearly nonsense, then I'll just give you 0. Okay, so if you write down the answer in test or homework, if you show no work or you write down something that's nonsense, then I'll just give you 0. So you still in tests you still need to show some work. However, you still need to show a little bit of work. You still need to show some work. Okay, some work. Okay, so if you show no work at all, in tests, if you just write down the answer and show no work at all, or if you write down something that's nonsense, then I'll give you 0. Okay, you still need to show some work, a little bit of work. Okay, something reasonable. Okay, let's do number 2. Okay, so this is Homework 1 PDF file, the Homework 1 PDF file number 2. And again, this is a question. This question is about finding the straight line that crosses 2 points. Okay, again, this question is about finding the straight line that crosses 2 points. So, so find the equation of the straight line that crosses 2 points, that crosses the 2 points 0, 2 and 2, 3. Okay, find the equation of the straight line that crosses these 2 points, 0, 2 and 2, 3, and then afterwards, again, roughly sketch the graph of the straight line. Okay, roughly graph the straight line. So roughly sketch the graph. Okay, roughly graph the straight line. Okay. 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 So. Okay. And again, this is an illustration of principle 1. Okay. Again, this is an example of principle 1, which says that 2 points determine a unique straight line. Okay, again, this is an example of principle 1, which says that 2 points determine a unique straight line. Because what do we have? We have 2 points. We have 2 points. We have the points 0, 2, and we have the point 2, 3. And remember, whenever we have 2 points, okay, so 0, 2, and 2, 3. Okay, so remember, whenever we have 2 points, principle 2 says 2 points determine a unique straight line. Principle 2 says that 2 points determine a unique straight line. So again, if we have 2 distinct points, then there's one and only one straight line passing through those 2 points. Okay, there's one and only one straight line passing through those 2 points, namely this straight line. Okay. And what the question asks us to compute the straight line. Okay, the question asks us to compute the equation of this straight line. That's what the question asks. Okay, so towards computing the straight line, towards computing the equation of the straight line, again, let's compute the slope. And to do that, we have a concrete formula for the slope, which is the slope formula. So by the slope formula, by the slope formula, we have a concrete formula for the slope, and that is the slope m is given by y2 minus y1 over x2 minus x1. And what's x1, y1, and what's x2, y2? Well, we can take this point to be x1, y1, and we can take this point to be x2, y2. We can also reverse this, but let's do it this way. Let's do it this way. So we take this point to be x1, y1, and we take this point to be x2, y2. So then we plug in these 2 points. Plug in this x1, y1, and this x2, y2 into this slope formula. And then we get that this is y2 is 3, y1 is 2, x2 is 2, and x1 is 0. Okay, so we plug that data into the slope formula. This is what we get. And now let's simplify. Let's continue computing. 3 minus 2 is 1. 2 minus 0 is 2. So then the slope m is 1/2. Okay, the slope m is 1/2. And then, okay, so then what do we have? We have the slope of the straight line, and we have 2 points on the straight line. We have the slope of the straight line, and we have 2 points on the straight line. So then, to compute the straight line, we can just use the point slope formula. We can just use the point slope formula to compute the straight line. So, by the point slope formula, the equation of the straight line is y minus d equals to m, the slope m, times x minus c. And we know what the m is. M is the slope. M is 1/2. And what's CD? CD is just any point on the straight line. Okay, CD is just any point on the straight line, so we can take this point to be CD, or we can take this point to be CD. We can take either one of these 2 points to be CD. Let's take this point to be CD. Let's just take this point to be CD. Okay, so plugging in this CD and this m equals to 1/2, this slope equals to 1/2 into this point slope formula, what we get is y minus d, d is 2, y minus 2 is equal to the slope m is equal to 1/2, which is 1/2, times x minus c, and what's c? C is 0, c is 0. Okay, and then if you want, in tests and homework, you can stop here. So you can stop here, okay? In tests and homework, this can be the answer. You can stop here, and this can be the answer, okay? So can I stop here? In tests and homework, this would be perfectly fine as an answer. But let's nonetheless continue. Let's nonetheless continue computing. So if we continue computing, this is 1/2 times x, and the left-hand side is y minus 2. And then we can just bring the minus 2 to the right-hand side, so y is equal to 1/2 x plus 2. So in tests and homework, this will be an acceptable answer too. So in tests and homework, this is an acceptable answer, and this can be an acceptable answer too. So both of these answers can be acceptable. You can stop here if you want, or if you want, you can stop here. Okay, and what's the second part of the question? The second part of the question is to graph that straight line. For the second part of the question, so by the way, any questions? Any questions? Okay, so this is the solution to the first part of the question. Any questions? Any questions? Okay, no questions? Okay, so now let's do the second part of the question. The second part of this question is to just graph the straight line. Okay, so to graph the straight line, this is what we can do. Okay, so we know that these 2 points, 0, 2, and 2, 3, are points on the straight line. So then the graph looks like this. So take this to be the x-axis. Take this to be the y-axis. So the point 0, 2 should be over here approximately, and the point 2, 3 should be approximately over here. So this is 0, 2, this is 2, 3. And the straight line is just a unique straight line connecting these 2 points. So this is the straight line. So this is y equals to 1/2 x plus 2. So that's the graph of the straight line. Okay. Let's do the next question. Okay, let's do the next question. So let's do the homework 1 PDF file number 3. Let's do the homework 1 PDF file number 3. So homework 1 PDF file number 3. So this question asks us to find the slope, the x-intercept, and the y-intercept of a certain straight line equation. So determine the slope. You determine the slope, the x-intercept. Determine the slope, the x-intercept, and y-intercept of this straight line equation. Of the straight line equation 7y plus 12x minus 2 is equal to 0. By the way, let's call this equation over here a star. Okay, so for future references, let's call this equation star. So the homework 1 PDF file number 3 asks us to find the slope, the x-intercept, and the y-intercept of this linear equation, of this straight line equation. 7y plus 12x minus 2 is equal to 0. Okay, so that's what the question asks us to do. Okay, so let's first compute the slope. To compute the slope, we want to take this linear equation, we want to take the straight line equation and put it into the standard form of a linear equation. Okay, we want to take the straight line equation and put it into the standard form of a straight line equation. Because once we place this into the standard form of of a straight line equation. Once we've placed this into the standard form of a straight line equation, or the standard form of a linear equation, it's very easy to read the slope. It's very easy to read the slope. The slope is just m. Okay, so what we want to do is we take the linear equation star, which we call star, or the straight line equation, which we call star, and put it into the standard form of a straight line equation. Put it into the standard form of a linear equation. Because once we put it into standard form, it's very easy to read the slope. The slope is m. The slope is this m over here. Okay? Okay, so towards putting this into standard form, first bring the 12x minus 2 to the right. So if we do that, we get 7y is equal to, bringing the 12x to the right, that's minus 12x. Bringing the minus 2 to the right, that's plus 2. Okay, so what I did was I took towards putting equation star into standard form, I put the 12x minus 2 to the right. So I get minus 12x plus 2. And then towards taking the linear equation, the straight line equation, and putting it into standard form, I need to clear the 7. I need to remove this coefficient 7. So to remove this coefficient 7, I divide both sides by 7. I divide both sides by 7, and dividing both sides by 7, I get y equals to minus 12 divided by 7, x plus 2 over 7. So then, now this equation is now in this form. This equation is now in the standard form of a straight line equation. It's in the standard form of a linear equation, and it's now very easy to read the slope. It's very easy to read the slope. The slope is minus 12 over 7. The slope is minus 12 over 7. So let me write the answer over here. Slope is equal to minus 12 over 7. Okay, that's the slope. Okay, so that's the answer to the slope. It's minus 12 over 7. Okay, it's very easy now to read the slope. It's minus 12 over 7. Okay, that's the slope. Okay, now let's find the x-intercept. Now let's read the x-intercept. Now remember from last time's lecture? Yeah, remember from last time's lecture, how do you find the x-intercept? How do you find the x-intercept? From last time's lecture, the x-intercept is the point on the straight line where y is equal to 0. Okay, from last time's lecture, the x-intercept, the way to find the x-intercept is that it is the point on the straight line where y is equal to 0. So you plug y equals to 0 into the equation star, and you solve for y. Plug y equals to 0 into star, and you solve for x. Sorry, solve for x. Okay, plug y equals to 0 into this equation and solve for star, right? Because the x-intercept from last time, the x-intercept is the point on the straight line where y is equal to 0. So plug y equals to 0 into the straight line equation, into this equation star, and solve for x. Okay, let me check to see if the writing is clear. Okay, it looks like the writing is clear. It looks like the writing is clear. Okay, so plug y equals to 0 into star and solve for x. So plugging y equals to 0 into star, we get 7 times 0 plus 12x minus 2 is 0. And this is just 0. So we get 12x minus 2 is equal to 0. So then, isolating the x, we bring the 2 to the other side, so 12x is equal to 2. Continuing to isolate the x, we divide both sides by 12, so x is 2 over 12, which is the same as 1 over 6. So then, the x-intercept is just x is 1 over 6, and y is equal to 0. 1 over 6, 0. 1 over 6, 0. Okay, that's the x-intercept. Okay, now let's find the y-intercept. Let's find the y-intercept. Okay, so let's compute the y-intercept. So we're trying to find the y-intercept. Now remember from last time how to find the y-intercept of a straight line. So from last time, the y-intercept is the point on the straight line where x is equal to 0. Okay, so from last time, y-intercept is the point on the straight line where x is equal to 0. So then you plug x equals to 0 into the equation of the straight line, into this equation star, into star, and you solve for y. And solve for y. Okay, so from last time, the y-intercept of the straight line is the point where x is equal to 0. It's the point on the straight line where x is equal to 0. So then to find the y-intercept, you plug x equals to 0 into the straight line equation, and you solve for y. So you plug x equal to 0 into star, so you get 7y plus 12 times 0, right? 12 times 0, because we're plugging x equals to 0, minus 2 is 0. Okay, you plug x equals to 0 into star, so you get 7y plus 12 times 0. X equals to 0 is minus 2 is equal to 0. So this becomes 0. And so we get 7y minus 12 minus 2 is equal to 0. Okay, 7y minus 2 is equal to 0. And so continuing to isolate the y, let's bring the minus 2 to the right. So we get 7y is equal to 2. And then continuing to isolate the y, divide both sides by 7. So you get y is 2 over 7. Okay, y is 2 over 7. So then the y-intercept is, okay, so the x-coordinate is 0, and the y-coordinate is 2 over 7. So that's the y-intercept. Okay, so this is the y-intercept. Okay, so now let's do the next example. Now let's do the next example, which is the next example is homework 1, the homework 1 PDF file, number 4. Okay, the next example is homework 1 PDF file, number 4. So that's the next example. So we need to find the straight line parallel to y equals to minus 3x plus 1, which passes through 1, 1. So find the straight line parallel to the straight line equation y equals to minus 3x plus 1, which passes through the point 1, 1. Okay, find the straight line that's parallel to this straight line equation. Y equals to minus 3x plus 1. Find the straight line which is parallel to the straight line equation. Y equals to minus 3x plus 1, which also passes through the point 1, 1. Okay, Now, if you have a straight line, which is if you have two straight lines which are parallel, then they're going in the same direction. Okay? If you have two straight lines which are parallel, then they're going in the same direction. So if you have a straight line which is parallel to this straight line, it's going in the same direction, so then it has to have the same slope. It has to have the same slope because slope gives direction. Slope gives direction. So then the slope of that straight line has to be -3. It has to have slope -3. So the slope of the straight line is the same as the slope of this straight line, which is -3. Right? If you have straight lines which are parallel, then they're going in the same direction. So if you have a straight line which is parallel to this straight line, it's going in the same direction, so the slope has to be the same. The slope has to be -3. Right? The slope has to be -3 because slope determines direction. Okay? Slope of a straight line tells us the direction of the straight line. So you have a straight line that's going in the same direction as this straight line. Its slope has to be the same as the slope over here, which is -3. So the slope of that straight line has to be -3. And so note that we are in the situation of principle 2. We're in the situation of principle 2. A point in a direction determines a unique straight line. A point in a direction that determines a unique straight line, right? So we have a point, 1, 1. You have this point, 1, 1 on the straight line. And we have a direction. We have the direction. We have a slope -3. Okay, we have a slope -3. We have a direction. Right? Because slope gives us direction. So we have a point and we have a direction. And remember what principle 3 says, a point in a direction determines a unique straight line. A point in a direction determines a unique straight line. Meaning there's one and only one straight line crossing this point and going in this direction. Okay, there's exactly one straight line crossing this point and going in this direction, namely this straight line. Okay, so we're in principle 2, and basically this question asks us to compute the straight line. This question asks us to compute the equation of the straight line. Okay, so let's compute the equation of the straight line. So to compute the direction of the straight line, we can use the point-slope formula. Okay, to compute the equation of the straight line, we can just use the point-slope formula. So by the point-slope formula, the equation of the straight line is, okay, let's write down the point-slope formula. Y minus d equals to m times x minus c. And we know what m is. M is the slope. Okay, m is the slope. M equals to -3. And what's CD? CD is just any point on the straight line. CD is any point in the straight line. So we can take this to be CD. We can take this to be CD. Okay, we can take this CD to be this point, right? Because CD is any point on the straight line. So plug in this data m, and plug in this CD into the point-slope formula. Plug in this data into the point-slope formula. Plug in this m and this CD into the point-slope formula, and we get y minus d, d is 1, is equal to m. M is -3. Okay, m is -3, so -3 times x minus c, and what's c? C is 1. And by the way, in tests and homework, you can stop here. Okay, you can stop here. Okay, in tests and homework, you can just stop here. Okay, in a test, you can just stop here. But let's continue computing anyways. Let's continue computing anyways. So then, y minus 1 is equal to distribute this -3 over this multiplication over this -1, so it's -3x plus 3. And bring this -1 over to the right, so you get y equals to -3x plus 4. Okay, so this is an answer, and this is also an answer. Okay, in tests and homework, you can stop here, or you can stop here. Okay, let me see if I did it right first. Okay, it looks like I did it right. It looks like I did it right. Okay, so in tests and homework, you can stop here. Okay, this can be the answer, or you can stop here. This can be the answer too. Okay, let's see if I did this right. Okay, it looks like I did it right. I did it right. Okay, so now let's do the last question in homework 1. Let's do the word problem. Let's do the word problem. Okay, let's first write down the word problem. So, let's do homework 1 PDF file number 12. Okay, let's do the homework 1 PDF file number 12. So, a city's population was 30,700 people in the year 2000, in 2000 AD. And it is growing by 850 people per year. And it is growing by 850 people per year. Okay, so city's population was 30,700 people in 2000 AD, and that population is growing by 850 people per year. The first part of the question asks us to give a formula for the city's population P as a function of the number of years T since 2000, and make sure to give units. Give a formula for the city's population P as a function of the number of years T since 2000 AD. And that's the first part of the question. And you should give units too. You should always give units. So let me just not write this down. And the second part of the question asks us for the slope of the formula and interpret this as a rate of change. Give units and interpret this as a rate of change. What is the slope of the formula? I just write slope, give units, and interpret as rate of change. The third part of the question asks, what is the population predicted to be in 2010? What is the population predicted to be in 2010 AD? Okay, what will the population be in 2010 AD? And then the last part of the question asks, when is the population expected to reach 45,000 people? When is the population expected to reach 45,000 people? Okay, let me read this again just to make sure I got this right. So a city's population was 30,700 people in 2000 AD, And the population is growing by 850 people per year. So then, the first part of the question asks us to give a formula for the city's population P as a function of the years T since 2000 AD. The second part of the question asks us for the slope, give units and interpret as a rate of change. The third part of the question asks us how would this model, for this model of population growth, what is the prediction for the population in 2010? And the last part of the question asks, for this model of population growth, when is it expected for the population to reach 45,000 people? And when is the population expected to reach 45,000 people? Okay, looks like I wrote it down right. Okay, so now I'm gonna have to erase a lot of this stuff, by the way, because we don't have a lot of room. But first, before doing the question, let me say two things. Okay, so I'm gonna erase. The first thing is that for all word problems in this course, when you write down the answers, you should remember to write down the units. Even when I don't say units, for all word problems in this course, whenever you write down the answers, remember to specify the units. Even if I don't say the units, you should specify the units. Okay. So if you don't specify the units, then you will lose points. If you don't specify the units, then you will lose points. Or if you specify the units incorrectly, then you will lose points. Okay, so that's the first thing to note. Note, when answering word problems, okay, for any word problem in this course at all, and there in the future there will be a bunch of word problems, maybe even a lot of word problems. For all the word problems in the course, including the many word problems in the future, when you're answering them, always remember to write down the correct units. Okay, if you don't write down the units, then you will lose points. Okay, or if your units are wrong, then you will lose points. So when answering word problems, please write down the units. Okay, if you miss the units, if you forget to write down the units, then you lose points. Okay, so that's the first thing that I say. Okay, so this is an important thing for all the word problems in this course. The second thing is that whenever I try to answer any word problem at all, the first thing I do is I specify the variable of interest. Okay, I always write down precisely the variable of interest. Okay, whenever I do any word problem at all the word problems in this course, or any word problem in any situation, any other situation, the first thing I do is I always specify the variable of interest. Okay, in any word problem that I do, I always begin by specifying the variable of interest. And the reason for that is that by specifying the variable of interest at the beginning, then I make precise and clear in my head, in my mind, what the situation is. Okay? I make things precise and clear inside my head. Okay, so in all word problems that I do, I begin by specifying the variable of interest, because and even when that is redundant or very easy, okay, in many cases it may be very redundant or very easy to see what the variable of interest is, but I always, at the beginning, precisely specify the variable of interest, because it makes the problem very clear and very precise inside my head. For instance, it makes very precise what the units are. And sometimes in some questions, the units can be tricky, okay? And there are other reasons too. So no matter what word problem I'm confronted with, no matter how redundant or trivial it is, I always begin by specifying precisely the variable of interest, just to make things precise and clear inside my head. So now in this word problem, much of which I already erased, what's the variable of interest? What's the variable of interest? Well, in this word problem, the variable of interest is population. Okay, we're interested in population growth. We're interested in making future predictions of population. Okay, we are interested in making future predictions of population as a function of time. So the variable of interest is population. We're interested in population growth. So more precisely, the variable of interest is PT, which is the city's population as a function of time t in units of years since 2018, since 2018. So the variable of interest is city's population t years since 2018. Okay, if you look closely at the question, in particular if you look at the first part of the question, you see that this is the variable of interest. We're interested in the population of the city t years since 2018. Okay, that's the variable of interest. And the first part of the question basically asks us to compute this. The first part of the question asks us to find a precise formula for PT, for a precise formula for this function PT. That's the first part of the question. So part A, asks us to find a precise formula for PT. That's what part A is. Find a precise formula for PT. And okay, so what do we know? By the way, how long has this been? Wow, 1 hour and 21 minutes. It's longer than I thought. We know that the city's population was 30,700 people in year 2000. But remember, T is in years since 2000 AD. So year 2000 corresponds to T equals to 0. Okay, year equals to 2000 corresponds to T equals to 0. And we know that the city's population was 30,700 in year 2000 AD. So it's 30,700 people in T equals to 0. So T equals to 0. The population was 30,700. And we know that the population is growing by 850 people per year. The population is growing by 850 people per year. So if we move forward by 1 year, the population is growing by 850 people per year, so then we add 850. If we move forward by another year, the population is growing by 850 people per year, so then we add another 850. If we move forward by another year, the population is growing by 850 people per year, so we add another 850, and so on and so forth. So then we see that PT is, we start at year t equals to 0 with 30,700 people. And then we add 850 people per year. Okay, in the first year, we add 850 people. After another year, we add another 850 people because we're adding 850 people per year. So after this, the next year, we add another 850 people because we're adding 850 people per year, and so on and so forth. So it's 850 T. And what are the units? The units is people. And if you want, you can also write T years since 2018. Okay? So that it's enough to write this many people. And let me say that some homeworks were handed in already, and in those homeworks, they forgot to specify the units of people. They forgot to specify the units. Remember, you always need to write down the units for all your answers to word problems. For word problems, always write down the units. And some people who handed in their homework already didn't write down the units, so then they'll lose points. So then they'll probably lose points, okay? Okay, okay, so I'm really going over time. It's 1 hour and 24 minutes. So then what I'm going to do is I'm just going to talk about the second part of the question, and then I'm going to stop. Okay, I'm just going to talk about slope, and then I'm going to stop. Okay, so so B. What is the slope? And interpret this, and give units and interpret the slope as rate of change. So you can just read off the slope from here. The slope is 850. Okay, so the slope is 850. And the units for the slope is people per year. Units for the slope is people per year. Okay, that's the units for the slope, is people per year. And what I'm going to do is I'll explain why the slope is people per year in a few minutes. I'll explain why the slope is people per year in a few minutes. Let me just interpret this. This just says, let me just interpret the slope. This slope just says that the city's population increases by 850 people every year. Okay, the city's population increases by 850 people every year, per year. That's what this slope means. Okay, so this slope just means city's population is growing by 850 people every year, per year. Okay, so that's the interpretation of the slope. Okay, I'm just going to, and since I've gone massively over time, okay, I'm like 11 minutes over time already. What I'm going to do is I'm going to help you build some more intuition. Instead of doing the remaining two parts of this question, I'm going to help build intuition by drawing a picture. So I'm going to help build intuition by drawing this picture, by drawing a picture. So here's a picture, just to build intuition. And the intuition will also explain why the units for slope is people per year. Why the units for slope is people per year. Okay, so here's the picture for the intuition. Okay, so here's the intuition. Okay, so what's the slope? The slope is 850. And you can think of this as 850 is just 850 over 1. And you can think of the top is in years, and the bottom, the top is in people, is in units of people, and the bottom is in units of years. So 850 people over 1 year, 850 people over a year, 850 people over 1 year. So that's the slope. So rise is delta P equals to 850 people, and run is equal to delta T, which is 1 year. Okay, so rise is delta P, which is 850 people, and run is delta T, which is 1 year. So rise over run, 850 people over 1 year, 850 people per year, rise over run, rise over run. And this is a good way of building intuition for why slope is rate of change. This is a good way of building intuition for slope as rate of change. So this is good intuition for slope as rate of change. This is good intuition for why rise over run, or the slope, is rate of change. And this is also intuition, and this will also give you an explanation for why the units are people over year. Okay, this will also give you a picture for why the units for slope is people over year. Okay, so let's sketch the graph of PT. Let's sketch the graph of PT. So if we sketch the graph of PT, so then the horizontal axis is in units of t, is for the input variable t, and the input variable t is in units of years. Is in units of years since 2018. Years since 2018. Okay, so the horizontal axis is for the input variable t, and the units for the input variable t is years since 2018. And the vertical axis, is in output variable p, and the units for the output variable p is in years, is in people. The units for the output variable p is in people. Okay. So the vertical axis is for the input variable t, and the input variable t is in units of years since 2018. And the vertical axis is for the variable p, and the variable p is in units of people. And the function pt should, roughly speaking, look like this. So this is the function pt. So pt is equal to 30,700 plus 850t. Okay, can you still read this? Okay, you can still read this. Okay, and then you can see what rise over run means. And this is a very good. You can see what the slope means, or what the rise over run means. And this is a very good explanation of slope as rate of change. What the slope or the rise over run means is that at any point in time, say at this point in time, if you move forward by 1 year, then the population increases by 850 people. That's rise over run or the slope. That's the meaning of rise over run or the slope. At any point in time, if you move forward by 1 year, the population increases by 850 people. Okay, that's true no matter what point in time that you start with. If you start at this point in time, you move forward by 1 year, then the population rises by 850 people. Okay, so at any point in time, say at this point in time, if you move forward by 1 year, then the population rises by 850 people. Okay, at any point in time, you move forward by 1 year, the population increases by 850 people. So this is a good illustration of slope as rate of change. This is a good illustration of how rise over run gives us rate of change. And this also explains the units for the slope. This also explains why the units for the slope is people over year. Because for rise, the units for rise is in units of people, and the units of run is in units of years. The units of rise is in units of people, and the units of run is in units of years. So then the units for rise over run should be in people over year. So the units of rise over run or slope is people over year. So this gives an explanation for the units of slope. Okay, I've gone massively over time. I'm over time by 18 minutes. So then what I'll do is I'll stop here. Okay, so thank you for your patience. I'm stopping right now.